In an open-loop control system, the stepper motor must be dimensioned to safely drive the maximum load. For this reason, a safety margin of 20% is normally included, but this margin is effectively wasted as energy in the application. If the load decreases, the open-loop motor cannot adjust, resulting in even greater energy loss. In closed-loop mode, the current is continuously adjusted by the load control loop. This means that at least 20% of the reserve is saved. In many cases, a power reserve of 35 to 50% is included to account for tolerances in other components. Since the application usually operates under partial load, energy costs are significantly reduced with closed-loop control. A simple belt drive with rollers with a diameter of 0.04 meters, a friction factor of 0.3, and a speed of 191 revolutions per minute requires a maximum torque of 1.48 Newton-meters for a 20 kilogram load, including 0.17 Newton-meters at no load. Since more than 80% of these motors are used in applications with varying loads, closed-loop technology offers significant potential for energy savings, thereby also helping to conserve resources and protect the environment. Thanks to efficient current regulation, the motor generates less heat and stays significantly cooler. The motor bearing is also better protected against wear due to the reduced temperature rise. At high ambient temperatures, the duty cycle and the expected service life of the bearing are substantially increased. A temperature reduction of 15 degrees Celsius can extend the bearing life by up to 50%. With a 20% safety reserve and a design based on a 20 kilogram belt load, even a total weight of just 5 kilograms exceeds the power reserve, and the open-loop drive will stop without any indication. In contrast, the closed-loop stepper motor can drive this load without difficulty thanks to its overload reserve. If short torque peaks occur during normal operation, for example due to a brief increase in friction of more than 20%, an open-loop motor will stop despite its safety reserve. In contrast, the closed-loop motor can handle such short-term overloads without difficulty. Open-loop operation therefore requires significantly more testing during commissioning to ensure safe operation. If longer torque increases occur during normal operation, for example due to component damage or increasing friction from wear, the open-loop motor will stop even with a 20% safety reserve. In contrast, the closed-loop motor can handle this overload and simultaneously issue an error message. However, if the adjustable current limit is exceeded over a defined period, the closed-loop drive will also switch off to protect the motor and the system. The resonance frequencies in an open-loop system depend, among other factors, on the external load. The greater the torque reserve, the stronger the resonance impulses, up to the point where the motor may come to a standstill. In closed-loop operation, however, the motor's energy supply adapts to the actual load. Since there is no excess torque reserve, virtually no resonances occur. The noise generated often reflects the resonance behavior. The smaller the torque reserve, the stronger the system damping and the lower the operating noise. In critical applications, especially with variable speeds and changing load profiles, open-loop operation often requires complex design measures. In closed-loop operation, by contrast, virtually noiseless performance is possible even at low speeds and under varying loads. Stepper motors achieve a positioning accuracy of 1.8 degrees or 0.9 degrees even in open-loop operation. Without load, they maintain an angle tolerance of plus or minus 5%, provided that both phase currents form perfectly equal vectors over the full 360-degree electrical field. Approximately 75% of the deviation results from winding resistance differences due to manufacturing tolerances and from sensor resistance in the driver. The remaining 25% is attributable to mechanical inaccuracies. Under unsymmetrical load conditions, the maximum deviation is plus or minus 0.9 degrees. Step angle errors of plus or minus 5% and plus or minus 3% for 90% of motors can be guaranteed in full step operation with balanced switching and symmetrical load. However, in microstepping, unbalanced switching, including AD converter accuracy, as well as unsymmetrical loads, have a disproportionately large effect on the error. Microsteps therefore cannot reliably reproduce positioning accuracy without significantly increased effort. The integrated encoder in the closed-loop stepper motor, with a resolution of over 4,000 increments per revolution, not only meets the specified step angle tolerance of plus or minus 5%, but also, particularly under varying loads depending on direction and magnitude, ensures repeatability with an angle deviation of plus or minus 0.09 degrees. Load-induced angle fluctuations are thus reliably compensated, and even microsteps of up to 1/10 step can be precisely monitored. In closed-loop operation, microstep resolutions of up to plus or minus 0.09 degrees per step can be reproduced, resulting in significantly lower position deviations and higher repeatability. This is particularly relevant for testing equipment and machines requiring high axis accuracy, such as scanning or dispensing processes. For linear motion with a screw lead of 2 mm, this corresponds to a linear resolution of plus or minus 1 micrometer per step. Through load angle scanning, the closed-loop motor determines the current rotational angle, optimally timed when the rotor changes its angle with its external mass. This allows the transient response at the point of lowest kinetic energy and the reversing time, by utilizing the kinetic energy in the new rotation direction, to be significantly reduced. In open-loop operation, unfavorable timing, depending on the external load, can adversely affect stop and reversing times. Due to shorter transient and reversing times, faster acceleration and deceleration, and higher speeds, since open-loop operation requires a safety margin for these, positioning times can be reduced by up to 40% depending on the movement cycle. Particularly in production machines, shorter cycle times can significantly improve competitiveness, making closed-loop operation the clearly more efficient drive solution. The higher the speed, load inertia, and torque variation, the greater the time-saving effect compared to open-loop operation. Due to varying load and speed conditions, open-loop operation can produce oscillation amplitudes of differing magnitudes. These negatively affect smooth operation as well as the service life of bearings, belts, gears, and other components. In closed-loop operation, the current vector continuously adapts to the load, while PE controllers and filters effectively compensate any remaining oscillations. In some applications, a limit switch may be difficult to access, space may be lacking, or its use may be undesirable for cost reasons or to reduce potential sources of error. Open-loop operation is generally unsuitable for this position or path detection task, whereas closed-loop operation allows the path to be detected precisely and the torque to be variably adjusted up to the holding torque. In torque mode, the closed-loop stepper motor behaves like a spring, with the spring characteristics adjustable via a potentiometer. The motor provides a stable force even when resisting an opposing load while stationary. As the opposing force decreases, the motor rotates and adjusts its torque proportionally up to the set current or torque limit. This makes the closed-loop stepper motor ideal for winding, tensioning, and pressing applications.